And that's why dogs can't fly. Oh, that was a good one. All right. So anyway, the ideal gas law. We know this is the ideal gas law, and we know that the N represents the number of moles. So we can use the ideal gas law in stoichiometry, right? Stoichiometric equations or calculations. So we're going to do example 10.4 on page 304. And that says a chemist is decomposing KCl. We're going to see in a minute that it's solid KCl. They're going to say that. The chemist is decomposing KCl. And what does that mean when we say we decompose something?
Breaking it into its individual elements.
Exactly. So we're going to what we're going to have on this side of the equation is going to be potassium, right? And the other thing that we need to worry about in Cl, and what we need to worry about whenever we do a decomposition and we break it into elements, is we have to pay attention to whether or not we have any what? Like, is this correct? Are we done?
No.
No? What are we missing?
The chlorine is supposed to be a diatomic ion.
It's a homonuclear diatomic, right? So the chlorine gas always appears in pairs. So we've got 7 of those, and we have to continue to remember that. That concept's not going away, right? So it breaks down like this. And so then we've got to make sure it's balanced. We've got to put a 2 in front of this and a 2 in front of this. And so now we've got a balanced chemical equation. So a chemist is decomposing KCl into solid potassium and chlorine gas. So they tell us this is a solid, and they tell us this is a gas. All right? And they say if he does the reaction at a pressure of 1.02 atm, pressure is 1.02 atm, and a temperature of 24.3 degrees Celsius, T equals 24.3 degrees Celsius. What volume of chlorine gas will he make with 50 grams of solid KCl? So we have 50 grams, I'm going to write that down here, 50 grams of KCl, and we want to know the volume of Cl2. Right? That's what we're trying to figure out. All right. So where does stoichiometry figure into this? Well, we have an equation that we could plug in some of these values and we could figure out the volume, right? And that equation is the ideal gas law equation. And if we rearrange that, solving for V, then we get, PV equals nRT. If we want to solve for V, we divide both sides by P. And so we get V equals nRT over P. And so what we have already given to us is we have the pressure, we have the temperature. Can we use the temperature as it's given to us?
No.
You have to change it to Kelvin. And so how do we do that? We add
273.15.
273.15, and so that's going to equal 297.5 when you round and take significant figures into account, which I'm not making you guys do. You're welcome. So that's the temperature that we have to use. So we've got temp taken care of. We've got pressure taken care of. We know R because that's a constant, but we need N, right? And we need N of what? We need the number of moles of what? KCl. This is the ideal what law? Gas law. So Cl2 is our gas in this equation, and that's what we're trying to find. They asked us for what volume of chlorine gas will he make with 50 grams of solid KCl, right? So chlorine is what we're interested in. We're interested in the volume of chlorine. And that makes sense because chlorine is the only gas in this equation, and this law only works for gases, right? So the thing that we're missing is right here. We're missing the number of moles of chlorine. We're not given the number of moles of chlorine. We're given the number of grams of chlorine. But we have a little drawing that you've seen before where you take the grams of one substance and you can convert it to the moles of that substance, and then you can convert it to the moles of another substance. And then if you need to, you convert it to the grams of that other substance, right? So we can go from grams of KCl, since we have the balanced chemical equation, to moles of KCl, and from that we can convert to moles of Cl2. And that's what we're lacking in this equation to be able to calculate the volume. So does everybody understand what we've got to do? All right, cool. So the first thing we have to do is go from grams of KCl to moles of KCl. So 50 grams of KCl, the way that we do that is we look at our periodic table and we grab the atomic mass of potassium and chlorine, and we see that 1 mole of KCl is going to contain, if we've done this so many times, I'm not going to continue to write it down every time. You should have that down now. You should be able to figure out the molar mass of a compound, right? So it contains 74.55 grams of KCl. So if we punch that in our calculator, we get 0.671 moles of KCl. But that's not what we need for our equation here. We need the moles of chlorine gas in our equation. So how do we convert that to moles of chlorine gas? Well, we take the moles of this and we multiply that using the stoichiometric relationship. We know that 1 mole of chlorine gas is equal to 2 moles of KCl, right? So then our KCl units cancel out here, and we're left with 0.336 moles of CO2. So we're almost there. Now we can actually, we've got all the values that we need to plug in for the volume, to our equation to give us the volume. So the volume of chlorine gas is going to be equal to the number of moles of chlorine gas, 0.336 moles, times the ideal gas constant, which is 0.0821. Okay, I knew that, of course. Just checking you. Make sure you didn't think it was 1.2. What's the temperature? We determined that the temperature was 297.5 K. You got to convert it to Kelvin. And then the pressure is given to us as 1.02 ATM. Are all of our other units correct? I mean, do we need to convert anything else, or are we good? How do we know? Like, if they had given this pressure in torr, could we just plug it in torr, or would we need to convert it to ATM? We needed to convert it. Why?
Because of the unit.
Because the unit of that guy, right? Because that guy has units that contain liters, ATMs, moles, and Kelvin, right? So we got to make sure our unit matches the ideal gas constant. Yes?
So we can use R to determine whether we have our units correct, whether or not we have our units correct.
Yes. Yep. And in fact, R is the whole, because of R, that's why we know what the unit for volume is going to be. What's our unit for volume going to be when we do the calculation? Liters, right? All right, so we plug all that in our calculator and we get 8.05 liters. All right? So yeah, make sure you know those units on the ideal gas law constant, because that's going to be important. And it's going to tell you what you have to convert the rest of them to. And it's also going to tell you what your final unit is. All right, any questions about that? Okay, so if we take the ideal gas law and we solve for the number of moles. So like just in this equation here, we solved for V. So let's say we solve for the number of moles. How would we do that? Well, we would divide both sides by RT. This is what you had to do on the quiz, right? You would divide both sides by RT. RT cancels out over here, and so we see that the number of moles is equal to PV over RT. All right, if we do that, we can see another law that's referred to as Avogadro's law. Avogadro should seem familiar because
he had a number.
He had a number. That's right. He had a number. You may know what that number was. Avogadro's number?
I was looking for it a second ago.
What is that? Avogadro's number is what a mole is, right? So just like a dozen is 12, a mole is 6.02 times 10 to the 23 of something. That's Avogadro's number. So that his name should already be familiar to us. And Avogadro's law says this: equal volumes of all gases at the same temp and pressure have the same number of molecules or atoms if no molecules in gas. Because some gases, that are floating around, they're not homonuclear diatomics. If it's a homonuclear diatomic like oxygen, and you've got two oxygen atoms that are bound together to form an oxygen molecule. Well, some gases, it's just the substance floating around, just individual atoms, right? That's why you've got that statement in parentheses at the end there. So what does Avogadro's law have to do with rearranging this equation? I'll let you finish writing and then I'll tell you. This is my opportunity to take a sip of my Dr. Pepper. All right. Think about it. If we've got several gases floating around, right, in an environment where the pressure and the temperature are the same, right? So you've got gases floating around out here in the atmosphere. The atmospheric pressure is the same. The temperature in the room is the same. You've got oxygen, you've got nitrogen, whatever, right? If you have the same volume of those gases, so let's say I have 500 milliliters of oxygen and I've got 500 milliliters of nitrogen. Since pressure and temperature are the same, then how many moles of nitrogen and oxygen do I have? Well, I'm going to have exactly the same number of moles, right? Because if I figure it out for oxygen, right, my calculation is going to be, atmospheric pressure is like around 1 atm, right? We got some, we know that our volume is 500 milliliters, I said. We know R is 0.0821, and I said, it's in the room, so it's all at the same temperature. Let's just say that our temperature here is 22 degrees Celsius. We can't say that. We'd have to say it in...
Yeah, and wouldn't you have to say the volume is liters, not mils?
I would, thank you. All right, we'll do 500 liters. Thank you so much. 500 liters, and so instead of, we'll just say 290, we'll say 295 K. All right, so let's say that's the temperature. If I've got 500 liters of oxygen or 500 liters of nitrogen, I'm going to come up with the same N, right? Mm-hmm. So you see if pressure and temperature are the same, as long as we've got the same amount, the same volume of gas, the number of moles of that gas are going to be the same. So what, Mr. Walker? Right? Why do we care? All right, well, because there's this cool thing that we can do only with gases in chemical equations, all right? And I'm going to define that in this statement here, which says when all substances of interest, I'm going to underline that because we're going to explain that a little more fully in just a moment. So when all substances of interest in a chemical equation are gases, if P and T are constant, the chemical equation gives you the volumes of those gases. I'll let you write that down and we'll talk about it. right, so what that means is this. What bearing does that have on working in chemical equations? Well, it means if we have a chemical equation like this, 2H2, which is a gas, plus O2, which is a gas, yields 2H2O as a gas. And what we've said is the way that you read this chemical equation, what if we said that these numbers in front of each of the compounds represents the number of what? Moles, right? So we say we would read this chemical equation as 2 moles of hydrogen gas plus 1 mole of oxygen gas yields 2 moles of H2O gas, right? But what this statement here says, because of what we got from Avogadro's law, is that if all the substances that we're focusing on in the chemical equation are gases, we can actually say that not only do these numbers mean moles, number of moles, but we can also say that these numbers will give you the volumes of those gases. So it would actually be accurate for us to say, if we take 2 liters of hydrogen gas and combine it with 1 liter of oxygen gas, that will give us 2 liters of H2O gas. Right? All of these have to be gases. It only works for the gases in the equation. You can have other things in the equation, but this is a true statement for the gases in that chemical equation. You could change it to milliliters. You could say 2 milliliters of H2 gas plus 1 milliliter of oxygen gas will yield 2 milliliters of H2O gas. So that's pretty cool, right? For gases only, you could say that this, not only does the chemical equation tell you the relationship between the moles, but it also tells you the volumetric relationships. It tells you the relationship between the volumes of the gases in the chemical equation. All right? So if I'm telling you that, then obviously we're going to use it in a problem, right? We're going to do some math with that. Yay! Exactly. This is trying to decide if this is, I think we can still use this a little longer. We'll try and see. All right, so let's do an example. And that example is on page 306. And it's example 10.5. And it says a chemist is converting iron 3 oxide to iron via the following reaction. So Fe2O3, that is a solid plus 3O, it's a solid plus 3CO carbon monoxide as a gas, and that's going to produce 2 Fe as a solid plus 3 CO2 as a gas. So don't look at this and say, well, what we just learned has no bearing on this because we have substances in there that aren't gases. If we focus only on the gases, if we're only interested in the gases, then what we just learned about saying that these numbers could refer to the volume of the gases, we can still use that information, depending on what we're trying to find. So what they ask us here is if the reaction consumes 8,615 milliliters of carbon monoxide, so if we have 8,615 milliliters of this substance, what volume of carbon dioxide is produced at the same temperature and pressure? So how many milliliters of this will we get at the same temperature and pressure? And remember, all of this started with a look at the ideal gas law when the pressure and the temperature are the same. So because of what we just learned, then we can say, we can convert this, we can convert 8,615 milliliters of CO, 2 milliliters of CO2 by saying that, just like we did in stoichiometry before, where we said 3 moles of CO2, right? We said based on this equation, we can say that 3 moles of CO is equal to 3 moles of CO2, right? That's what we've learned previously. But what we just learned also told us that we can say 3 milliliters of CO equals 3 milliliters of CO2, which is what we're going to use in doing this conversion. So 3 milliliters of CO2 equals 3 milliliters of CO in our chemical equation. And so if we have this many milliliters of CO, we also have the same number of milliliters of CO2. Yes.
And that only applies for milliliters, not like just liters.
It could be liters as well. That's what I was saying. It doesn't matter the volume. Whatever volume you start with, you just want to use the same volume throughout your calculation. Okay? So, like for example, you know, in the medical field, they use cc's a lot. Sorry, something just happened with my back. I don't know what it is. Some of you are walking around like this. cc's, right? What does cc stand for? Anybody know? Cubic centimeters. So cubic centimeters is another unit for volume, right? So we could say 3 cc's of CO equals 3 cc's of CO2. As long as you stick with the same unit, then you can make those relationships based on the chemical equation, if we're dealing with gases. Okay? All right, any other questions? All right. Let's see. What do we want to talk about now? Dalton's. Again, just to reiterate, that only applies. We can't say this many milliliters of this substance equal that many milliliters of that. It only applies to gases in the chemical equation. Let's talk about Dalton's law of partial pressures. Did I turn this off? I guess I did. Dalton's law of partial pressures. All right. This law says that the total pressure, if you have a mixture of ideal gases, and we talked about ideal gases last time, and we said that a lot of these equations we're going to look at are applied to ideal gases, hence the name ideal gas law. And we said when we talked about ideal gases that it's really kind of a theoretical term, right? You can't really truly have an ideal gas because you have to be able to have a gas that has a volume of 0, and that's not possible because it's matter, and so it has to take up space. But we said that gases can, under certain conditions, behave very close to ideal. And so, what were those conditions? Do you guys remember?
0 degrees Celsius and 1 atm.
Say that a little louder.
Was it 0 degrees Celsius and 1 atm?
It was, in order to behave ideally, they needed to be near or above 0 degrees Celsius, or they needed to be near or below a pressure of 1 atm. So near or above 0 degrees Celsius and near or below 1 atm. So as long as it meets that criteria, then we can say that a gas is going to behave ideally. All right? And so what this law tells us is that for a mixture of ideal gases, if you've got a bunch of ideal gases that are in an environment or in a container mixed together, you could say this. You could say that the total pressure of the gases for that mixture is equal to the partial pressure of the individual gases in the mixture. So in other words, in this equation here, it's where P1 is the pressure of gas 1, P2 is the pressure of gas 2, etc. So you can take the individual pressures of all the gases together and add those together to figure out the total pressure of the entire mixture. So P1 equals the partial, if I use that term, partial pressure of gas 1. So the total pressure is the sum of the partial pressures. let me just write this down. For a mixture of ideal gases, that's true. There's something else that we can say if we have a mixture of gases like this. I want to give you this definition of a mole fraction. And a mole fraction is that's the concentration of a given gas in a mixture of gases. And we define the mole fraction for a given gas. For gas A, the mole fraction is, we'll start by that. The mole fraction is, for gas A, is moles of A divided by total moles in mixture. Where are we getting bubbles? You guys thought I was going to make tea for the class today, right? You thought this little teapot was all about?
Well, it would be nice.
Nice
He's like, no, you said it.
cup of Earl Grey for everyone. Maybe some biscuits along with our tea. Tea and biscuits would be nice. All right, so moles of A divided by the total moles in the mixture will give us the mole fraction of A, the concentration of that particular gas. And the higher the number of moles, obviously the higher the mole fraction is going to be, so the greater the concentration. So the bigger this number, the greater the concentration is for that particular gas in the mixture. All right? So let's look at page 308, and we'll do a problem. We're not going to do everything in there. We're just going to do the first part because it's just kind of repetitious. But it says a mixture of a mixture of gases includes 15 moles of chlorine, 15 moles of chlorine, and 12 moles of argon. Argon's not one of our homonuclear diatomics, so I'll just write that as AR. And then 11 moles of oxygen. And so they ask us, what is the mole fraction of each gas? So we're just going to do the first one, the mole fraction of chlorine. And so to figure that out first, in order to determine the mole fraction, we've got to figure out the total number of moles, right? So let me make myself a little more room here. So the total number of moles in this mixture is, so total moles would be 15 plus 12 plus 11, which equals 23, 38, right? 38 moles. And then if I want to find the mole fraction of chlorine, the mole fraction of chlorine is going to be equal to the moles of chlorine, which it gives us as being 15, divided by the total number of moles, which is 38. And so we get a value of 0.395. Now notice our mole units cancel out, so we actually don't have a unit on the mole fraction there. But that represents the concentration. And since there's more moles of chlorine than there are of the other gases, if you look at the problem, you'll see that those numbers get smaller. The concentration is less for the other gases because there are fewer number of those gases in the mixture. Questions about that? That's pretty straightforward, right? I mean, you could probably fall asleep during this part and it won't really matter. Right? Okay, so let's move on to another way to define Dalton's law that now involves mole fraction. And so we can also say Dalton's law could be written like this. An alternate way to write Dalton's law would be XA, the mole fraction of gas A is equal to the partial pressure of gas A over the total pressure of the gases in the mixture. So two ways to define Dalton's law. This is another way to express Dalton's law. So now with all of that, let's do a more complicated example. The first example, example 10.7, is really just kind of like this. It's just a really straightforward one where you're just plugging in the values, and it says a mixture of gases. You have 567 torr of oxygen. You have 913 torr of argon, and you have 131 torr of fluorine. And it asks what's the mole fraction of each gas. So another way, just like we found the mole fraction in the previous example using the number of moles, we can now find the mole fraction using the partial pressures of each of them. So first we need the total pressure, and we get that by adding all these up. 567 plus 913 plus 131. So that gives us a total pressure of 1611 torr, right? And so, for example, I want to find the mole fraction of oxygen, which is a concentration of oxygen. The mole fraction of oxygen is going to be equal to the partial pressure of the oxygen over the total pressure in the mixture. So 567 over 1611 gives us 0.352. And we could do that for each of them. Again, there's no unit because the torr units cancel out here. So mole fraction doesn't have a unit there. But the next example is far more interesting. So let's move on to that one. What do you guys think? This is getting harder and harder to see, isn't it? We need to probably at the end of class see if we can dispose of this marker, because I don't want to continue to use it. So we'll see if the whole entire class can get an extra point today. All right. Again, I don't like to do that on film because if I hit a student, I just hate to hear the crying on the film, on the video. All right, so law of partial pressures. Let's just write these down. P total equals P1 plus P2 plus P3. And mole fraction can be represented as either moles of A over total moles, or, like we just learned, it can also be the pressure of A over total pressure, right? So we'll write that down before we erase all of this. Let's do the next problem. And the next problem says 50 grams of chlorine gas are mixed with 50 grams of fluorine gas. So we've got 50 grams of chlorine mixed with 50 grams of fluorine. Both are homonuclear diatomics, right? Right? You guys remember all the homonuclear diatomics? Yeah. Remember, if you look at your periodic table, you can remember those because it's the top 4 in column 7A. And you just need to make sure that you remember that hydrogen, nitrogen, and oxygen are also in that list, right? So if you can remember hydrogen, nitrogen, and oxygen, then it's fluorine, chlorine, bromine, and iodine. All right. So they give us the grams of each of those gases, and they say the mixture exerts a total pressure. So pressure total is equal to 3.56 atm. And then they say, what is the partial pressure of each gas? So what is PCl2 and PF2? That's what we're trying to figure out, right? So now this one's a little more complicated, and this one you're going to get this kind of problem. You're going to get confused on a test if you can't follow this. So if unless you're going to watch the video later, not the best time for sleeping right now. I'm just going to say that. All right. So what is the partial pressure? Well, here's what we know. Let me make a little more. These are kind of, put a line between these so we can kind of see each one. We're given grams of this substance and grams of this substance. From grams of each substance, we can calculate what? Moles of each substance, right? Just by using the periodic table, we can convert the number of grams to moles of each of those substances. If I figure out the moles of each substance, then I can determine what the total moles are that I have in my of gases, and I can figure out the mole fraction for each of those gases, right? And since it's asking me for the partial pressure, once I figure out the mole fraction, then I can use this formula, because I can determine, since I know the mole fraction then and they've given me the total pressure, I should be able to figure out the partial pressure for each gas. So that's going to be the path that we go down. We're going to first convert these to moles. Then we're going to plug that into here to get the mole fraction. Then we're going to use the mole fraction and the total pressure that's given us to find the partial pressure of each gas. Okay? That's the path that we're following. So make sure that you understand that. So actually for this particular one, we don't really need this equation because it's just not, it's not going to help us in figuring out what we need to know. So the first step is going to be to convert each of those to moles. So 50 grams of Cl2, 1 mole of Cl2 is equal to, we go to the periodic table, we say Cl has an atomic mass of 35.45. So we've got 2 Cl's, so we're going to say that's 70.9 grams of Cl2. And so that tells us that we have 0.705 moles of Cl2. 50 grams of F2. Again, we go to the periodic table. We see that fluorine has an atomic mass of 19. So 1 mole of fluorine gas, since there's 2 of them, is going to be equal to 38 grams of fluorine gas. And so when we punch that in, we have 1.32 moles of F2. All right. Now we can figure out the total number of moles in the system, right? In our mixture here, total moles is equal to 0.705 plus 1.32 to give us a total of 2.03. Right? So now we can figure out the mole fraction for each one. So now we know that xCl2 is going to be equal to the moles of Cl2, which is 0.705, divided by the total moles, which we calculated to be 2.03. So the mole fraction for xCl2 is 0.347. And then the mole fraction for fluorine is going to be 1.32 moles. The other number of moles we calculated, divided again by the total moles to give us 0.65. And again, those don't have, the mole fraction doesn't have units. All right, so we're almost there. We were asked for the partial pressure of each gas, right? So now we're going to use this final equation, but we got to rearrange the equation a little bit because we're not solving for the mole fraction. We already have that. We're solving for the partial pressure. So we're going to rearrange that equation. Instead of XA equals PA over PT for total, we're going to rearrange that to say that P partial then, the P of gas A is going to be equal to XA, the mole fraction of A, times the total pressure. Right? So that's the formula that we're going to use to calculate the partial pressure of each of these. So the partial pressure of chlorine then is equal to the mole fraction of chlorine, which is 0.347, times the total pressure, which they gave us at the beginning of the problem, 3.56 atm. And that's going to be equal to 1.24 atm. And then for the partial pressure of fluorine, we get what we calculated over here is our mole fraction, 0.65, times the total pressure, again, which is 3.56 atm, given to us in the problem. And that is 2.31. So these would be the answers to our problem. So that's a little longer process. Did I lose you anywhere along the way? Anything not make sense? You see why we had to take that path? Does that make sense? So you just need to understand these are related, and so there's all kinds of ways that I could sort of put these different equations together to form problems where you go down a particular path and you find a certain value. All right, if there aren't any other questions, then I'm going to move on. Going once, going twice. No? All right. I tried, guys. Where are my notes? There we go. I want to make sure I don't shortchange you guys and not give you your money's worth today. All right. Vapor pressure and boiling point. Cool. We can finally actually boil this. Do our experiment. Vapor pressure and boiling point. That'll be our last topic. Okay. Vapor pressure and boiling point. If we boil water, what happens? If you leave a pot boiling for a long enough period of time, what's eventually going to happen?
It's gonna
water's gonna
You lose all your liquid water, right? Because it turns into gas, right? It turns into gas H2O. It evaporates.
That's actually happened to my mom before.
Yeah? Where did my water go? Well, it's been boiling for 3 hours. So it will eventually evaporate, right? And that makes sense to us on the stove because it starts boiling. And what's actually happening when it's boiling is that water is beginning to turn into gas, and those bubbles that are forming, that's the water turning into gas, water in the gas state, right? And it's floating to the top and escaping from as it converts from the liquid phase to the gas phase. Well, what if you put a glass of water outside and you leave it there long enough? What's eventually going to happen to that glass of water if it doesn't rain? Huh? It's going to evaporate too, right? Did it ever boil?
No.
No? So if it evaporates outside, why is that even though it never boils? And the reason it does that is well, we've got a chart. Let's look at our chart on page 311. All right, our chart on 311 kind of shows us what we refer to as the vapor pressure of water. And as it turns out, all liquids do that. All liquids are going to evaporate if you leave them out like that in a container. So some of the liquid is going to begin to convert to a gas. And so what you have is, like gasoline, liquid gasoline, for example, you always have to be concerned about the vapors, right? Because the vapors are dangerous there. I mean, you can actually kind of see, like if you look at gasoline, it'll be sort of wavy as you look through it, right? Because of that vapor that's sitting on top of that liquid gasoline. What that is that's gasoline that's converted to gas, right? That's the vapor, just like you have water turns into vapor at the top there as it boils off. That's the vapor sitting on top of that liquid gas, and all liquids do that. And if that if that gaseous compound is sitting on top of the liquid state of the compound, then that gas is applying a pressure on top of that liquid that's there, okay? And that's what we refer to as the vapor pressure. And so that's what we have in our chart on page 311 for water. And we see that at various temperatures, even though the vapor pressure is really high because there's a lot of that turning into vapor when it's at 100 degrees Celsius, which is the boiling point of water, even at low temperatures, like 0 degrees Celsius, when water freezes and begins to turn into a solid, even then you've got some gaseous water sitting on top, right? Some vapor pressure that's present. It's low. It's only 4.6. Let me open that there. There we go. Only 4.6 torr of pressure versus 760 torr of pressure at 100 degrees Celsius. Did anybody notice the 760 torr at 100 degrees Celsius, and what does that equal to? Huh? 1 atm, right? So 1 atmosphere, which is like standard atmospheric pressure, right? That's roughly what we're at now is 1 atm, and so water on average will boil at 100 degrees Celsius, right? And so I'm telling you all of this because we're going to give you an actual true definition of the boiling point of a liquid, which we haven't been able to do before because we haven't introduced this topic of vapor pressure. But boiling point is actually, the boiling point of a liquid is actually the temp at which the liquid's vapor pressure is equal to the external air pressure. So once the vapor pressure equals the external air pressure, that's when you start to see those bubbles forming and the liquid will begin to boil. And these bubbles will float to the top. They're going to form at the bottom and float to the top because the pressure inside the bubble equals the outside pressure, the external air pressure. And so what's cool about that is as atmospheric pressure changes, so will your boiling point. The atmospheric pressure will affect the boiling point of your liquid. So the boiling point of water may be different depending on where you are. You know how it's like you've seen some recipes maybe that at high altitudes you have to do that recipe differently because the pressure's different at higher altitudes. And so the boiling point of water will be affected by the differences in the outside air pressure, the atmospheric pressure. And so we're going to do an experiment now. That's why I'm boiling this water here, to show you how that if you change that pressure in the system, how it will affect the boiling point. Okay? So let's see. Let's do one more example, example 10.8, and this is vapor. Let's talk about vapor pressure in Dalton's law. Vapor pressure in Dalton's law. All right. So, a chemist makes carbon dioxide according to the following reaction, it says. So, why are we talking about this? Well, so when we do these often in chemistry experiments, gases are collected. Yes? Yes, gases are collected, but if the chemical reaction takes place in water, the gas that's collected may include some water vapor, right? And so when that's the case, we need to use Dalton's law to try to subtract out the amount of water vapor that's there so we can actually determine how much of the gas that we collected that we were interested in, okay? So example 10.8 has to do with that. And it says, a chemist makes carbon dioxide gas according to the following reaction. And so it's C2H4. Somebody want to read that off to me?
C2H4O
What's aqueous plus what?
Plus NaHCO3.
What form is that in?
Solid.
Solid, okay.
And then that produces NaC2H3O2 in aqueous,
Okay.
plus H2O in liquid, and carbon dioxide in gas.
All right. Thank you. All right. Does that look good to everybody? So that's the chemical equation that they gave us. No stoichiometric coefficients on the front. Interesting. So if the chemist collects 2.4 liters of the gas produced, so the gas that came out was, the volume was 2.4 liters of the gas produced over the water in which the reaction took place at 30 degrees Celsius. The temperature was 30 degrees Celsius. And a pressure of 756.1 torr. How many moles of carbon dioxide were collected? And so we want to find moles of CO2 is what we're interested in. And so what we know from Dalton's law is that we've only got two gases here. Like I said, we collected this carbon dioxide gas, but the reaction took place in water, right? It was an aqueous solution right here, which means it's been mixed with water. And so we know that in addition to the CO2, which is the only gas that's produced from just these chemical compounds, we're also going to have some water in gas form. So we need to subtract that out. So we know that the total pressure of the system is going to be equal to the pressure of the CO2 plus the pressure of the water vapor. That's based on Dalton's law. Right? PT equals P1 plus P2 plus any other pressures of partial pressures of gases that were in there. Well, our total pressure, they told us, was 756.1 torr. We don't know what the pressure of CO2 is, but we do know by our table on page 311, and I will give you this, by the way, on the test. I'll give you the table. We know by our table on page 311 that at a temperature of 30 degrees Celsius, water has a vapor pressure of 31.8 torr. So this is 31.8 torr. So from that, we can calculate the pressure of CO2 and determine that it is 724.3 torr. Now, the problem asked us for what? Do I know? Number of moles of carbon dioxide. So we're focused on this gas right here. We don't want to know the number of moles of that. We have all of these values, and we've determined the pressure now of the CO2 gas specifically. Is there any formula that we know, given these values, that we might be able to determine the number of moles of a particular gas?
Ideal gas law.
Ideal gas law, right? So PV equals nRT, or if we solve for N equals PV over RT, right? So the number of moles is PV over RT. We've got V. We have a volume of 2.4 liters. We've got the temperature is 30 degrees. We need to add to that 273. Yeah, I was like, that's not right. Why is that not coming to me? All right. There you go, Elizabeth. 273.15, right? So we add that together, we get 303.15 Kelvin. So we've got volume, we've got temperature, we know the R constant, and we know pressure now, because we just calculated that. But our pressure is in torr, and we need pressure in ATM, right? So let's go ahead and calculate that. We know that 1 ATM is equal to 760 torr. So we multiply that conversion factor times the 724.3, and we get 0.953 ATM. 0.953 ATM. All right, so now it's just a matter of plugging in those values. N equals, P is our partial pressure that we calculated, which is this right here. We just figured out in ATMs. 0.953 ATM times volume, which is 2.4 liters, divided by R, which is 0.0821, times temperature, which is 303 Kelvin. And we just double check our units real quick because we remember the units of the ideal gas constant. And we got ATMs, liters, and Kelvin, so those match up. We should be good. And we punch that in our calculator and we get 0.092 moles. That's our final answer.